Dear students, in the last class we have to discuss about symmetric group and details about the S3, and I show the complete Cayley table of S3 group and find the inverse of the elements of this S3, and then show that the we have an inverse and this two elements is inverses each other and rest of them all are the inverse of itself. Identity, pi, and all these things. So now we continue today's class, and this today class we have to discuss the order of a permutation group, and if permit we have to discuss some other properties of a symmetric group. The order of a permutation for pi is equal to belongs to Sn is the smallest positive integer m such that pi to the power m is equal to identity, or we have to just say that this 1 or identity. So this is we can say that pi identity permutation pi to the power m is equal to we have a identity permutations. So we denoted this as a O of this throughout O of pi, and then let us see, we have to just say that this theta of this means we have to take a element of a x is equal to, you have a 1, 2, 3, and then pi theta we define the form of a theta of 1 is equal to 2, theta of 2 is equal to 1, theta of 3 is equal to 3, I defined previously is a pi this form. So now we have to just check this the identity of a permutation of this identity permutation. In this case we have a 1, 2, 3, 1, 2, 3, and clearly this is clearly not equal to the identity permutation. So we have to find the theta square, and the theta square is equal to theta into theta. Then we have a 1, 2, 3, 1, 2, 3, then 1, 2, 3. Sorry, this is we have to write into 1, 2, 3, and then we have a 2, 1, 3. Then is again 2, 1, 3. Now we take a composition 1, 2, 3. 1 goes to you have a 2 and 2, 1. 2 goes to 1, 2. 3, 3, and this is clearly the identity. So this is means theta is not equal to, but theta square is equal to identity. So this we can say that order of a this theta is equal to 2. So order of a this theta is equal to 2 clearly. So now we have to this also, if we have a pi is equal to this, then we say just check verify this is equal to what is pi square. So we have this pi is equal to x is equal to, we have to take a 1, 2, 3, 4, 5, and then we have a take is equal to 1, 2, 3, 4, 5, and then a 3, 4, 1, and we have a 5 and 2, and this is clearly is not equal to identity. Now we have to take a pi square, then is equal to 1, 2, 3, 4, 5. Now 3, 4, 1, 5, 2. Then you have a 1, 2, 3, 4, 5, 3, 4, 1, 5, 2, and this is clearly you have a 1, 2, 3, 4, 5. Then 3, 3 goes to 1, 2 goes to 4, 4 to 5, 3, 1, 1, 3. Then you have a 4, 5, 5 is equal to 2, 5, 2, and 2 is equal to, you have a 4, and again clearly not equal to identity. Now we take a pi 3, then you have a 1, 2, 3, 4, 5, pi square 1, 5, 3, 2, 4, and then you have a 1, 2, 3, 4, 5, and then we have a 3, 4, 1, 5, 2, 1, 2, 3, 4, 5, then 3, and then 3 goes to 3, 2 goes to 4, 4 goes to 2, 3, 1, 1 goes to 1, 4, 5, 5, 4, 5, 2, 2 is equal to 5. Again it's not equal to identity. Then we have to take a 5, 4, then we have a 1, 2, 3, 4. We have to take a 5, 3 into pi, and then we have to 1, 2, 3, 4, 5. 1 goes to 3, 3 goes to 1, 2 goes to 2, 2 goes to 4, 3 goes to 1, 1 goes to 3, 4 goes to 4, 5, 5 goes to 5, 5 goes to 2, again not equal to identity. Then we take a 5, 5 is equal to 5 to the power 4 into pi, and then we have a 1, 2, 3, 4, 5, 1 goes to 1, then 1 goes to 3, 2 goes to 4, 4 goes to 5, then we have a 3 goes to 3 and 3 goes to 1, then 4 goes to 5, 5 goes to 2, 5 goes to 2 and 2 goes to, you have a 4. Again not equal to identity, then we have to take a pi to the power 6 is equal to pi to the power 5 into pi is equal to 1, 2, 3, 4, 5. Now pi to the power 1 goes to 3 and 3 goes to 1, then 2 goes to 5, 5 goes to 2, 3 goes to 1, 1 goes to 3, then 4 goes to 2 and 2 goes to 4, 5 goes to 4, 4 goes to 5, and this is clearly identity. So we can say that clearly order of this pi is equal to, we have a 6, because pi to the power 6 is giving you a identity element. So this means we can say that this pi to the power m is equal to 1 is equal to 6. So order of a pi is equal to, we have to giving the 6 clearly. S3 has a, we have to just remark is this S3 is a non-abelian group, or we can say the non-commutative group. The subgroup of S3s are, we just said that E rho zeta, and then because inverse of these two are each other, and this is inverse of this E is clearly, and then product of these two again belongs to this set. So clearly this is a one subgroup of this, then this is also the inverse of each itself is there. So there is, these are the three subgroups. Since the closure property is satisfied and it is each is a finite subset, so subgroups of a S3 are these three are the subgroups except the trivial one. So now cyclic group of S3 is identity element generate Holzer set. Clearly rho is generated by this, so this is our subgroup. Rho is generated by this because rho square is equal to zeta and rho cube is equal to identity. Similarly zeta is generated by the same subgroups, so zeta square is equal to rho and zeta q power 3 is equal to identity. And then we have to just say that delta is generated by E and delta, delta square is equal to identity. Then gamma is also generated by this subgroup, and then pi is also generated by this subgroups. So the cyclic subgroup of a S3 are these are the cyclics generated by rho, generated by zeta, delta, gamma and pi, and also I is there. So these are the cyclic subgroup of S3. All are the proper subgroups of these, all are the proper subgroups of S3. S3 is itself, S3 is not cyclic, but there is a 6 all this, these are the proper subgroup, cyclic subgroups are there. S3 is not a cyclic, since order of S3 is equal to 6, but there exists no element of order 6 in this S3. So clearly we cannot find any element which is order is equal to 6, because this maximum order is equal to, we have a is equal to 3. So clearly the order of a rho is equal to 3. So from here we can say that the clearly order of rho is equal to 3, order of zeta is equal to 3, order of delta is equal to 2, order of gamma is equal to 2, order of pi is equal to 2, like this. So this is equal to clearly these two elements which are the order is equal to 3, and rest of them this identity of order 1, and all other 3 elements are order 2. So we clearly say that there is does not exist any element whose order is a 6, and so S3 itself is a not a cycle, but there is a some subgroup which are cyclic are there. So, does every permutation have a finite order? The following theorem provides the answer to this question. So, now the question is clearly this: does every permutation have a finite order? So, now we have to try to prove this. For pi belong to Sn, there exists a positive integer m for which pi to the power m is equal to identity. If we take a pi belong to the Sn and then some positive integer which is exist in this pi to the power m is given the identity permutation. Consider the proof, consider the list of powers pi, pi square up to and so on, and now because Sn is a we have to working into this form, since there are only finitely many permutations of any finite set. So, if we have a set is Sn is a finite set. So, if it is a finite set is there, then only finitely many permutations we can define into this. So, there exists means we at some stage some repetition is starting from there. So, after some point there is a this repetition should be starting into a within this list. So, if repetition is starting within list, so you can assume that we can suppose pi to the power r and is equal to pi to the power s for some r is less than equal to s lies between this. So, clearly if we have a pi, then we have to just say that inverse of a permutation exists. So, we can say that pi of r minus s and pi minus s is giving you a identity element. So, if pi minus I to the power gives identity element, that means we have to just say that at which some stage we have to find some positive number m can be written in the form of r minus s. So, m is equal to you have a r minus s because there are some integers, positive integers there. So, at this stage we can say that pi to the power m is you have a giving is the identity element. So, we can prove this theorem very trivially that for any pi belong to the Sn, and there exists a positive number m for which pi to the power m is giving you a 0. Now, we move to the next definition of the permutations is a orbit. So, what is orbit? So, pi let pi be a permutation of a set x. The equivalence classes in x determining by the equivalence relation is A related to B if and only if B can be written as a pi to the power n A for some n belongs to the z are called the orbits of a pi. So, pi is we have to pi is a permutation, then equivalence classes of a x determined by the equivalence relations. If we have just say A is related to B if and only if B can be written as a pi to the power n A for some n belongs to the z are called the orbit of this pi. So, consider the permutation this we have to in S8 we have to try find the what is the orbit of this. So, to find the orbit containing 1 we apply pi repeatedly, then we have to just say that 1 is mapped to 3 then pi and then 3 to we have to go to 6 and after 6 you just see that we have a repetition is a start and so on, this is going to this. This means we can say that simply this since pi inverse simply reverse the direction of the arrows of the chain. So, this we see that the orbit of we just change the pi inverse of this. So, reversing the this direction of this we have to just say that into this form. So, we see that the orbit containing 1 is 1, 3 and 6. So, similarly we have to now next we choose an integer from 1 to 8 that is not in 136 simply 2 and we say find the orbit containing 2. So, now by this we have just said that 2 to 8 and then 8 to 2. So, we have to again 2 to 8, 8 to 2 and we have to repetition is start again if we have to reversing this pi inverse is there. So, we have to just say that the orbit to 8 is 2 8. Finally, we have to find the element which is not the member of a one integer 1 to 8, that is not is 1, 3, 6 and 2 and 8. So, we have a left is 4, 4, then we starting from the 4. If we since these 3 orbit include all the integers from 1 to 8, to complete the list of the pi, we just say that we have a this is clearly we have a 4 pi to 7 pi to 5, then we have a pi to 4. What is this? Then we have a 7, we have a 5 and so on. So, another orbit is equal to 4, 7, 5. Now, you see all the elements of the integer 1 to 8 is containing in these 3 orbits 1, 3, 6, 2, 8 and 4, 7, 5. We have to just is one orbit is equal to 1, 3, 6, another is we have to just say 2 and 8, then we have a 4 goes to 7, 7 goes to 5, 5 goes to 4. So, this is a another orbit we have to set into this form. So, there is a another this is you see we have to write it as a cyclic notations of this. So, there is another common used to describe permutation known as a cyclic notation, and this is important of our theoretical advantages as it makes certain important properties of a permutations more apparently and easier to analyze. So, definition of a cyclic we have to just take, let k be a positive integer, a permutation pi be an element of Sn, then pi is called k cyclic of I1 to Ik. If pi can written as a I2 and then we have a I1 goes to I2, I2 goes to I3, Ik minus 1 Ik and Ik goes to 1. So, and that is we can say that pi of ij is equal to j plus I, j running 1 to k minus 1, and pi of I k is equal to I1 and pi of a is equal to a for any other elements 1 to n is there. So, we just say that pi of a is equal to a means another element we have to fixing from pi a to a. Whenever we have a ik is equal to pi 1 and then we have to I1, and then similarly pi of ij can be written as a ij of j plus 1 we have to. So, like this 1 is equal to 2, 3, 3, 2 is equal to 3, k minus 1 is equal to k and k is equal to 1 in this form we have to writing into the cyclic notation. In other word, permutation pi belongs to the Sn is called a cyclic if it has at most one orbit containing more than one element and the length of the cycle is the number of element in its larger orbit. So, cyclic notation we just simply other way also we can say that cycle it has a at most one orbit containing more than one element, and if it containing the orbits, the length of the cycle, the number of element in the largest orbit is called the length of the this cycle is there. For example, we will note that we have to, if pi is equal to we have a I1 I2 Ik, then pi can be written as I1 I2 Ik, then I2 I3 Ik, I1, and then we have to starting from again this can be written as a I3 I4 I k I1 I2, and then again we can write in the form of this I4 I5 and so on Ik I1 I2 I3 and so on like this. So, in the last we can write is Ij plus 1 Ik I1 up to Ik minus 1. So, this is the figure we can just say that I1 go to I2, I2 go to I3 and so on ik minus 1, and then ik minus n is equal to ik, and ik is equal to again by the I1. So, this is the we have to notation is a this is a this figure is showing that is a cyclic notation of the this cyclic group. Note that the only one cycle in Sn is the identity permutation and denoted by this, and if we let us S6, we have to the permutation is equal to assign the values can be systematically. We have a like this, we have to 1 goes to 2, 2 goes to 1. So, we have a 1 is the orbit 1 2, and then we have a 3 goes to 4, and 4 goes to 6. So, 3 4 6, and then we have a and 6 goes to 3, and then we have a orbit is a 5. And we just said that there is a 3 orbits are there, and this is a cyclic 1 2, and then we have a 3 4 6, and then 5 itself. So, assign the value represent systematically 1 and 2, when we have a 3 goes to 4, 4 goes to 6, 6 goes to 3, and that is a cyclic notation. And then these are the 3 orbit, and then this orbit is the largest orbit is equal to this, and there is an element is equal to 3. So, length of this cycle is equal to we called is a 3. So, instead of a Hilliard arrow, simply write into this form, and now we just simply removing this arrow, and generally we just write in the simply write as a 4 3 4 6 1 2, or other way also consider the another for example another permutation we have to consider into this form. So, here we have to simply is equal to you have a 1 5 2, and you have a 3, and another you have a 4 and 6. So, these are the 2 cyclic notations are there, and simply we have to just say that this is a cyclic representation orbit largest orbit, and this is orbit as a 4. So, this is the length is equal to 4, and this is length is equal to 2 is there. So, in the cyclic notation theta can be expressed into either this form or this form. Either we can write is equal to we have write it 2 3 1 5, or we can write is equal to 5 2 3 1, or we can write as equal to 2 3 1 5. Sorry, this we can write in the form of a 1 5 2 3, and similarly we just cyclic notation into we have to writing into this form is this. Since both of these notation clearly describe the function of a phi, so we can simply define this into a this form. Multiplication of a cycles can be understood by viewing the each cycles as a permutations that fix any symbol not include the cycle. So, we just said for example 4 6 can be through representing as a permutation is equal to into this, and then rest of them is equal to 1 goes to 1, 2 goes to 2, 3 goes to 3 in the cyclic notation. We representing for only cycle 1 6 4, 4 and 6 is equal to this form, and use this appropriate approach we can multiply cycles by interpreting them as a permutation written in array form. So, we just consider the following example as 8 pi is equal to this, we have this cyclic notation, and theta is equal to we have to writing into a this is the side when dealing the single digit of integer, it is common not to omit these commas between the digits. So, now we just try to find out the what is the cycle of a theta pi. So, pi theta into pi, so what is a theta? We have to theta pi is equal to we have to write in this form. This is we have to writing is equal to theta, and this is we have a write into this form is a pi. This is a pi, and this is we have a sorry this is equal to theta, and this is we have a pi. So, now we write one cyclic notation 1 2 3 7, and then we have a this is 1 2 2 7 1 7. Now, 2 is equal to we have a 7 7 goes to 1 1 goes to 3, and now 3 goes to 2 and 2, 2 goes to 7. So, this is clearly we have to just is equal to 1 7 3 and 4 8 and 5 this is 4 4 8 and 5 goes to 5, 5 goes to 6, 5 6's are there and 4 8 is there. So, clearly we have to write by the cyclic notations this pi of theta clearly written in this form. Today's lectures here, and then in the next class we have to continue this cyclic notations of this again. So, I just to stop today's lectures here. We continue into the next class up to thus again is a cyclic notations. So, thank you very much.